This was for 0, 1 loss. Now, is there a more general statement that we can make? Well, there is no complete general statement that we can make because, as we just saw, the simple decomposition of loss is equal to bias plus variance does not always hold, right? And in fact, what exactly happens is going to depend on the particular loss function. However, there is a somewhat more general statement that we can make that applies to a lot of loss functions, which is the following. The loss is equal to the bias plus a c, a constant c, times the variance. And when the bias is 0, c is always 1. Okay? So for a certain class of loss function, which includes the ones that we've been looking at, when the bias is 0, the loss is equal to just the variance. Okay? Not a big deal, but that preserves that additive decomposition. The interesting case, of course, is when the bias is not 0, then what is c? Okay? Well, for squared loss, we know that c is equal to 1, right? It stays, the loss is still bias plus variance. We just saw that for two-class problems, c is equal to -1, right? But we actually didn't see what happens for multi-class problems, right? What if I had, a whole bunch of different classes, right? Then just because two classes are different, just because A is different from, B, it could still not be equal to C, right? Well, in that case, C is minus the probability that Y is equal to T given that it's not equal to Y bar, okay? Again, the math for this is straightforward, right? But you have to multiply by that factor. So in some senses, it actually reduces the effect of the variance by that probability. For variable costs, right, which is actually an important case, right? Let's suppose you have an arbitrary cost matrix. Then this C is actually minus the ratio of two losses. The loss between T and Y bar and the loss between Y bar and T. If they're the same, this gets us back to being 1, but in general, they might not be the same. Okay? And so on. Any questions about this? Okay, so, last thing. Even more generally, right? Can you say something about not just particular loss functions, but about a very general class? Let's say all loss functions that are metrics, right? Metric means they obey the triangle inequality and so on. Okay? Yes, we can. So in particular, if a loss function is a metric, you can show that the loss will never be more than the bias plus the variance. So this is good. You measure the bias and the variance, and that puts an absolute cap on your loss. Okay? It also puts a minimum on the loss, and the minimum is the maximum of these two things, the bias minus the variance and the variance minus the bias. Okay? So a graphical way to look at this is that, here's, on the x-axis my loss, right? My bias puts me somewhere on that line, and then what I have is the variance, is kind of error bars around that. My loss could be at most the bias plus the variance, or at least it's going to be the bias minus the variance, right? So the quick thing to say is that your loss is going to be the bias plus or minus the variance. Okay? So there's this region that your loss could be in. So this doesn't, this is not an equality, but it actually still is pretty informative. Okay? All right, so that was bias and variance for you. Questions?
Do we compute bias and variance on the training examples only? Or?
Very good. So so this is all very nice, right? But now there's some logistical problems, right? We're going to ask you to, estimate bias and variance, in your assignment, right? How do you actually do that, right? I don't have the ability to generate infinite random training sets, right? So how might we do it? Give me a suggestion.
Cross-validation type of,
Yes, but here's a big problem, right? Is that when I do cross-validation, I reduce the size of my training set. And variance and bias change with the size of the training set, right? In particular, right, the variance very much depends on the size of the training set. Okay? So what might I do instead? Here's a hint. It's something that we saw when we talked about model ensembles.
sampling with replacement.
Sampling with replacement, right? Generate bootstrap replicates of your training set. Right? What we used in bagging. Remember when I said that bagging came from statistics and people use this to estimate, means and variances, in an unbiased way, right? You generate a training set of the same size as your real one, right? Except that it's a random variation of it because some things got duplicated, some things. In fact, this introduces a small amount of bias, but hey, it's all we can do, right? So one way to do this in practice is to generate, bootstrap replicates of your training set and take those as being your surrogates of generating new, training sets from your real process. which for things like estimating bias and variance is a pretty good approximation. Okay? Good question. More questions. All right, so